In the last decade, we optimized our stacks for milliseconds. We obsessed over database indexing, CDN edge caching, and minimizing payload sizes to ensure users felt an instant response. But then, large language models arrived, and the rules of physics for our architecture changed overnight. While a standard REST API call might return in 50 to 200 milliseconds, an LLM generation often takes several seconds, sometimes even a minute for complex reasoning tasks. This isn't just a minor delay, it is a fundamental break in the synchronous request-response cycle that nearly every modern web application is built upon. Integrating AI isn't just about adding a new endpoint, it is about managing a massive increase in latency that threatens to degrade user experience and overwhelm traditional backend structures. Today, we are exploring why AI is breaking your architecture and how to fix it.
To understand the latency, we have to look at the math of tokens. Unlike a database that fetches a row, an LLM predicts the next word, or token, one by one. We measure this with two critical metrics: time to first token, or TTFT, and tokens per second. TTFT is the processing delay, the time it takes the model to understand your prompt and start writing. Tokens per second is the generation speed. If a model generates at 20 tokens per second, a 500-word response will take at least 25 seconds of active connection time. This creates a long-tail request that holds your server resources open for far longer than they were designed for. If you have a standard server with a limited connection pool, just a few concurrent users can completely exhaust your available workers, leading to a cascading failure across your entire infrastructure.
This shift kills the traditional synchronous request-response model. In a standard setup, the client sends a request, the server processes it, and the client waits until the full payload is ready. With AI, that wait time is unacceptable. If a user sees a spinner for 10 seconds, they assume the app is broken. The architecture must shift from pull to stream. By using server-sent events or WebSockets, we can stream tokens to the front end as they are generated. This drops the perceived latency from the total generation time down to just the time to first token. However, streaming introduces complexity. You can no longer easily use standard HTTP load balancers that expect quick closures, and you must handle partial state on the front end, ensuring that your UI can gracefully render an unfolding thought without flickering. The most effective way to solve the latency crisis is to avoid the LLM altogether when possible. Traditional exact match caching doesn't work well for AI because prompts are rarely identical. Enter semantic caching. By using vector embeddings, we can check if a new user prompt is close enough to a previously answered question. If the semantic distance is small, we serve the cached response instantly. This transforms a 5-second wait into a 20-millisecond database lookup. Look at this comparison, a raw LLM call versus a semantic cache hit. Not only do you save on latency, but you also drastically reduce your API costs. However, you must carefully tune your similarity threshold. Too loose and users get irrelevant answers. Too tight and your cache hit rate drops to 0.
When you can't avoid the latency, you must hide it. Speculative execution is a technique borrowed from CPU design. While the LLM is generating, the backend can speculatively start the next steps, like prefetching relevant documents or preparing the next UI state. On the front end, we move beyond simple spinners to optimistic UI and multi-stage reveals. Instead of waiting for the whole response, we show the LLM's intent immediately. For example, if a user asks to generate a chart, we can render the chart container and axes instantly using local logic, while the LLM is still crunching the data points. This creates a perception of speed, even when the underlying process is slow. It requires a tight coupling between your AI logic and your component state.
To survive the latency crisis, your stock needs a new layer. We call this the AI gateway. This layer handles the heavy lifting that your main application server shouldn't: request retries, model fallback logic, rate limiting, and the streaming connections themselves. By offloading these to a dedicated gateway, your core business logic remains responsive. This architecture also allows for model routing. You can send simple queries to a fast, cheap model like GPT 3.5 or Haiku, and reserve the slow, expensive models like GPT-4 or Opus for complex reasoning. This multi-tier approach balances cost, quality, and most importantly, speed. The future of AI integration isn't just a better prompt, it's a better engineered system that treats latency as a first-class constraint.
In summary, the LLM latency crisis is a wake-up call. We can no longer build systems that assume an immediate reply. We must design for asynchronicity, embrace streaming, and implement intelligent caching layers. The developers who win in the AI era won't just be the ones with the best prompts, but the ones who build the most resilient, latency-aware architectures. Start by measuring your P95 TTFT, implement a semantic cache, and move your AI calls to a dedicated gateway. Your users and your servers will thank you.